and particularly using DAOS, right? So we're using DAOS for checkpointing and being able to do writing or lots of data products for this is for a science quality simulation that would run at Aurora's capacity scale, so greater than 80%. So a little background on what exactly is the application. So the application is it's called HACC. So it's a hardware accelerated cosmology code. And to just kind of give you an idea of what how HACC works, the illustration here is that of the density field. So this is the entire volume of the simulation. So this was a simulation that we recently ran on the Frontier system at Oak Ridge, but it demonstrates sort of a lot of the pieces that we are also using on Aurora. And particularly this at the bottom is the asynchronous I/O storage that we implemented. But just as a big picture, the way HACC works is we have a large volume and we're evolving particles in a cosmological simulation. HACC separates the force into a large long-range force and a short-range force. That technology is using a spectral solver and a direct particle interaction. And there's a volume decomposition that maps particles into discrete subvolumes. So where each MPI rank owns now some discrete subvolume of the simulation. And for the purposes of this talk, I think the thing to sort of focus on is that those particles are necessary for writing the checkpoint, right? So the simulation proceeds and through many, many steps, and then periodically, it will write a checkpoint, in case there's a machine failure and the simulation needs to restart again. So on Frontier, and like most systems, of course, they're initially not very stable, so we needed to checkpoint very, very frequently. In this way, we developed this multi-tiered I/O system, where we took advantage of the NVMe or the node local storage on Frontier, and we modified our checkpointing system so that now the MPI ranks local to a compute node can write a checkpoint per individual node, right? So collectively, all of the ranks on the compute node write one checkpoint file, one per node. And that is a synchronous file write to the NVMe. And now the way this is set up is that the simulation can proceed, right? And one of the ranks, so rank 0 on each node, so local rank 0 to each compute node, will then do will spawn a thread and do an asynchronous background copy to the storage system. In this case, on Frontier, it was Orion, but on Aurora, it will it's DAOS. And what I'll present is sort of the Aurora version of this. So the simulation that we're running on Aurora is actually a much bigger simulation than that Frontier simulation that I showed you. It's 23,760 cubed particles, and that is over 13 trillion particles. So the simulation on Frontier was 4 trillion particles. This is several factors larger. And the reason is because Aurora has a lot of memory. So we were able to take advantage of the very large memory footprint to increase our memory footprint to run on a system like Aurora that has this additional capacity. Simulation runs in 500 steps, and it runs a full range of in-situ analysis. So there's a rich set of products that come out of a simulation like this. On Aurora, this is running with 8,100 ECBs, right, exascale compute blades, and we run in a configuration of 1 MPI rank per GPU stack. So as you guys have seen throughout this workshop, the Aurora has 6 PVC GPUs, per compute node. Each of them can be individually accessed per stack. So effectively, you see 12 devices. We estimate that this entire simulation will take about 500 hours of wall time, or sorry, 50 hours of wall time using all of the 8,100 nodes. And just to refresh refreshing your mind, the HPC environment, so Aurora's ECB has 2 Xeon CPU Max processors, 64 gigabytes of HBM, 512 gigabytes of DDR per CPU, so collectively about a terabyte of DDR. Like I said, 6 data center Max GPUs, and what we'll make use of is Aurora's has a TempFS file system on each compute node, accessed via the TMP directory. And we're using 128 node DAOS cluster, which I believe right now is called DAOS user. A lot of the things I'm going to say about DAOS are changing and being updated, so please always consult the documentation. Right, so what makes this challenging, right? So what makes I/O at scale for a particular simulation like this challenging? Well, just using 8,100 ECBs with that number times 12 compute ranks, all kinds of interesting things start happening. Things start to behave differently. With 13 trillion particles, that is approximately 500 terabyte checkpoints. So at this scale with 8,000 nodes, at this particle resolution, each checkpoint is half a petabyte roughly, which is, if you depending on what how long you expect, what the mean time between failures are for the system, and the time it takes to run each individual simulation step, you need to start to calculate, okay, well, how often and how, do I need to be writing checkpoints? And given that these checkpoints are extremely large, you're placing a lot of load on the file system. Like I said, things start to become trickier. So these 500 simulation steps, at least in the early part of the simulation, or we say in the early universe, from the benchmarks that we've done on scaled down versions of the problem, take about 6 minutes per step. And this time is affected by imbalance. And as the simulation progresses, the simulation becomes more clustered, and sort of the time it takes to resolve these steps slowly increases. But roughly something you can keep in your mind, at least for the purpose of this talk, is that things take between, say, 6 and 10 minutes to each step, to complete each step. So in situ analysis is also performed. Like I said, we do a lot of data analysis as the simulation is running. And that's performed roughly at about 100 of the time steps. So we take 500 simulation steps, 100 of those, we're doing some kind of complex analysis. And there are data products associated with each of those analysis steps. And those are small to medium-sized files. So we're generating these enormous half petabyte files to write checkpoints, and then and that may be done very, very frequently. So every step or every couple steps. And 100 of those 500 steps, we're doing these analysis and we're writing now data of various sizes, small size, medium size, depending on the analysis that's being performed. We estimate that roughly what we need to keep at the end is about 4 petabytes of storage for all of the data products, minus the checkpoint. So the strategy that we're using, sort of in the big picture, is that the collection of ranks that are local to a node, right? So like I said, we run with 1 per device, so 12 MPI ranks on Aurora, the configuration, 1 per stack, PVC stack. Each group, right? Each node, each of the ranks, MPI ranks local to the compute node, use mmap to collectively write to one file in tempfs. And after that's done, then one of the ranks, or the head rank for the node, will then copy that file to DAOS. So we'll spawn a thread, we'll asynchronously copy, and the rest of the ranks can immediately proceed to keep going through the simulation. Right, and so we use the POSIX IO interface for DAOS to do that. So a little more explicit about exactly what that workflow looks like. So like I said, 12 MPI ranks use this memory map or mmap. And this is kind of baked into the IO library that we use in the code to basically overwrite. So this is kind of something that we specialized for Aurora, but based on the sort of pattern that we used on Frontier. So we overwrite a shared file that's in tempfs, and we set this up with mmap to avoid having to go through POSIX system calls. So particles. So what happens is during the checkpoint, particle blocks are directly written to this mapped region or copied to this mapped region. And the file itself looks like some checkpoint name with a .mvram extension. I mean, this is the pattern of the file that the naming convention that we're using, and so that we can always just overwrite the file. And the idea is that the first time we create this mmap file, the pages aren't exactly assigned. I mean, it's sort of a lazy sort of after pages are touched. So the subsequent writes to that file are then very, very fast, right? So the operating system doesn't have to do the page walks again. So this is very fast in our experience. And then the copy to the DAOS container using the POSIX support is done with a DD command. So notice that we use also the LD preload of the intercept layer, right? So this lib PIL for DFS. What that is I don't know if it was already talked about here, but this is an intercept layer for POSIX calls that turn into DFS commands. So it makes the whole operation much smoother. Basically eliminates going through the system calls through the kernel. And then we specify the number of blocks for optimizing the transfer. And all the POSIX is done with diffuse. So there's no double buffering that's required because the amount of compute that we're doing exceeds the time that it takes to do the copy. So I'll show the results in a second. And so the DAOS configuration that we're using on Aurora, like I said, we're using POSIX via the diffuse mount. So the mount point that we use is actually also on the temp directory. But when you mount the DAOS container using the mount, basically what you see is a directory local to each compute node. And we use the LD preload library, or the like I said, that manages the POSIX streaming through DD. So we execute DD as a normal system command, but using this this library, this intercept library, it makes the whole copying faster by intercepting all of the POSIX operations and creating DFS commands, basically. Then the pool container class that we're using was this EC16 P2GX. Basically, this is the erasure coding, 16 data plus 2 parity. And we use the CRC for, we turn on CRC for verification, 128 kilobyte, the EC cell. So a lot of these things, I mean, it's important for you to understand, I guess, adjusting the cell size based on the type of erasure coding that you have set up. This is all very important to affect the performance. So for us, this was us experimenting a little bit to find exactly these settings. And likely in your code, depending on if you're writing very large files or you're writing a lot of very small files, the particular settings that you use for your container might give you different performance. In our case here, we're really concerned about the checkpoint files, which are actually are very large, and roughly on the order of 50 gigabytes per node file. So like I said, we were writing basically 500 terabyte collectively checkpoints, but each node is generating its own approximately 50 gigabyte file. Right. Okay. Yeah, so some results, right? So it's rather straightforward, the setup that we have. We run the simulation, we're writing these very frequent checkpoints. They're about 50 gigabytes. We're writing everything to tempfs, which is in memory, taking also advantage of the very large memory available on Aurora. And of course, the write speed that we get to DDR or tempfs is extremely fast, right? So that initial step, of course, this number is very, very high because it's split, sort of embarrassingly across the entire machine. But we see in doing that 237 terabytes per second, right? So that's if you think about collectively 8,100 nodes writing 50 gigabytes, all concurrently writing basically to RAM, their own local RAM. It's extremely fast, right? And so that's why that number is so high. The asynchronous data copy to DAOS, right? So this is the one rank per node that now is doing that single copy to the DAOS container. And remember, that's happening asynchronously. That's a background thread that's being spawned and doing the transfer. And so in essence, the simulation is proceeding. That's still happening quite quickly at about 3.75, what we measure terabytes per second. And taking, at least in this example that I'm showing, 111 seconds, so slightly faster than 2 minutes. And given, like I mentioned before, our time steps are taking probably 6 to 8 minutes to complete, then the entire cost of writing to the persistent storage system to DAOS is hidden. So great, right? So the key observation is that our 375 terabytes per second is significantly faster than the DAOS bandwidth. The checkpoint is basically completely hidden. And we were able to achieve DAOS copy at 3.75 terabytes per second on all 8,000 nodes. I think we were probably some of the first teams to actually run DAOS at this particular scale. The readback from DAOS was also very high. So of course, we intuitively think that should be much faster than the write time. Indeed it is. So we measured 7.6 terabytes per second, significantly faster than the write. And our effective IO bandwidth or effective IO overlap was very, very good, right? So over 95% of our checkpoint time is completely hidden behind the compute. So we were very happy once we get everything working. We spent a lot of time debugging, right? So there's a huge collaborative debugging that we closely worked with DAOS engineers with. Some of the things that we discovered over time were leftover agents, daemons that are running on some of the compute nodes. So we've worked with LCF and operations to try to identify things, improve cleanup scripts. DAOS, when we do the diffuse mount, we use there's a system command called clush. Some of the ways that that's configured, was very noisy, very verbose output. Again, when you're doing things at scale of 8,000 nodes, these things start to become very important. So some optimizations to those scripts we helped identify and have improved. The diffuse mount themselves, so the mount itself with on the full system scale pretty much was taking a very long time. So again, some work with the engineering team to try to improve that. So initially taking 20 minutes, I think we've gotten that down to maybe around 5. Within DAOS, so the DAOS pool disconnect times were also taking an exceedingly long time. I think DAOS opened up a support ticket to improve this. Probably, I think this may have been fixed on subsequent releases of the software. And stuff that you wouldn't see, that we won't see as users, but metrics, that sort of didn't make sense within DAOS itself. And DAOS team was also able to identify that and work on some of those things too. So quite a bit of work, during our effort in trying to get those results. A lot of work went with the engineering team to try to identify bugs and issues with DAOS and try to resolve them. Just a short summary. So we have this hybrid system of mmap and writing to tempfs, and we get these very, very high speed checkpoints and this asynchronous data copy with DAOS. We were able, through container configuration, tuning the properties and parameters, and using the strategy of this asynchronous copy, we're able to basically completely hide our compute or our copy with the compute. And yeah, and on Aurora, we were able to scale to 8,000 nodes of DAOS and write measured, close to 0.5 petabyte checkpoints, and sustained writes of 3.75 terabytes per second, and reads practically twice that, right? So 7.6. Yeah, and yeah, I make mention of all of our teams. So like I said, we've worked quite extensively. Our team, application team, is pretty heavily involved with all of this. But the DAOS team, Johan, Alex, Samir from LCF, Paul Kaufman, Kevin Harms, and all of our HACC team, we're pretty deep in the weeds on all of this, and trying to find problems in the system that happen at scale that are sort of very difficult to resolve. Yeah, that's the last slide I have. Happy to take questions. Yeah.